So in other words, what people have done before is to look at the effect of the whole troposphere. And now we are trying to separate it, the effect from the PBL and also the effect above the PBL. Okay. So this is the summary of that part. So what we find is without topography, so let's say these are the horizontal and vertical advection within PBL and above PBL. Now, when we look into these terms separately for below PBL or the planetary boundary layer and above planetary boundary layer, what we are seeing is that there is a 40% decline in precipitation, which was due to reduction in horizontal advection and vertical advection above the planetary boundary layer. And this is very important because people normally think most of this convergence was happening in the boundary layer, but modeling results is suggesting that significant amount actually happens above the PBL also. I mean, 60% comes from PBL, which is still the dominant, but 40% is not negligible. It's actually quite significant that is coming from above the PBL. So obviously, horizontal advection and vertical advection above the PBL can have significant impact on the maritime continent precipitation. Okay. So basically, what we learned from this topography experiment are the following. One is free tropospheric moistening processes are significant. When I say free tropospheric, I basically mean atmosphere above the planetary boundary layer, where the frictional effect is very, very small. So therefore, higher vertical resolution above the PBL may be very important. So this is a very, I would say, new idea in the sense that people normally try to put too many layers in the PBL and neglect what is happening above PBL. Now that may not be true in maritime continent. So if you want to reproduce the precipitation over the maritime continent, your numerical model should have actually a lot more vertical levels above the planetary boundary layer as well. Okay. And topographic influence is more dominant above 1,000-meter elevation. So it's not clear why the answer is 1,000 meter. So something might be a very interesting topic for example, for a master's or PhD thesis, why this particular layer or the level was the determining factor. We really didn't get into much more detail into that. So therefore, representation of the topography at local and regional scale may be very important along with the model resolution. So model resolution is one of the major factors in terms of capturing the precipitation in the maritime continent. And the last part we didn't talk about, but the simulated bias in model precipitation over ocean may actually come from its bias over land from high topography. So if somehow the high topography is not well represented in your model, particularly over the Kalimantan, then that may actually lead to bias in precipitation over the ocean. Okay? And this is very, very clear from all our experiments that we're seeing, particularly for the Kalimantan topography. Okay. And the last part is really interesting, and it's a fairly new study that we have been doing, where we are looking into role of precipitation-induced surface heat flux, and I'll explain it, on the diurnal cycle of precipitation. So if you look at modeling results over the maritime continent, so this is an example of timing of maximum precipitation. So the top panel is from a model, global circulation model or global climate model, and the bottom panel is from a satellite. Okay, so the green means early in the day, and red means later in the day, let's say. So this is like around 9 to 12 in the morning, and this is like in the afternoon and evening. So what you see in models is that it rains much, much earlier in the model, almost like 3 to 6 hours earlier than what you actually see in observation. So TREAM is all red if you look at it, and here it's all green. So that means model is actually producing rain much earlier. So there are major model weaknesses. For example, there is overestimation of precipitation over land, which I didn't show it here. precipitation peak is too strong and earlier than observed. So these numbers are actually much, much earlier compared to what you see in the observation. And precipitation peak is at the same time everywhere, unlike observation. So if you look at the land, it's all green, meaning that everywhere it's raining around noon at 12 p.m. Whereas in the actual observation, you can see both green and red, meaning that rainfall is distributed over time over the maritime continent islands. Okay. So the question that we are asking is, what controls the amplitude and timing of peak diurnal precipitation over the islands in the maritime continent? Okay. So obviously, factors that control diurnal cycle of precipitation, the main thing is the land-sea temperature contrast. Because your land is so much warmer during the daytime and ocean is cooler compared to the land, you actually have a land-sea temperature contrast. So that brings moist air to the land, and then you actually have precipitation over the islands. So by and large, the land temperature or the land surface temperature is determined by surface heat flux, meaning that how much energy is coming to the land surface and how much energy is getting out of the land surface. So there are four major terms. One is short wave, that is coming from the sun. Long wave, some long wave is getting out from the surface but also being re-emitted by the atmosphere. So there is a net long wave radiation. You also have sensible heat flux, which is basically whenever you have evaporation, your land surface gets cooler, correct? Because it needs those latent heat of evaporation. And then there is a sensible heat flux, which is just the difference between the land surface and the air above. So if there is a temperature difference, then the warmer surface will actually lose heat to the atmosphere. So these two are heat loss. This one is a heat gain, and long wave is also a heat loss. So you have three heat loss term and one heat gain term. So this is really a standard way of calculating the surface heat flux. So what I'm going to argue today is that this is not enough for maritime continent, and we should include another term which can be very, very important, and I'm calling that a surface sensible heat flux due to precipitation is actually neglected everywhere, and I'm going to argue that we should not neglect it for the maritime continent, and I'll explain why. So if you are not familiar with this term, QP, so this is what it means. When the rain falls on the surface, whether it's a land surface or ocean surface, it actually cools down the land surface or the ocean surface. And the reason is your raindrop temperature is cooler than the land surface temperature or the sea surface temperature, correct? So this is simply because the raindrops are cooler than the land surface. And so if you mix it, it will actually cool down. But this particular mechanism is actually not included in any model. But given the fact that maritime continent receives so much of precipitation, you'd expect that this term may not be negligible. And in fact, if you look at the literature, there is enough evidence that this term is actually not small. So for example, Cronin and McFadden around 156 east and 0 degree north, so which is right at the equator, found that it can be in the order of several hundred watt per meter square. Whereas, for example, sensible heat is order of 40-50 watt per meter square. So this can be really, really large. So there is already enough evidence that this should not be neglected in the maritime continent. So our basic hypothesis is the following. And this is really the important part of this last part. So if you introduce this sensible heat flux due to precipitation, it will cool the land surface. So there is no doubt about it, because the raindrop temperature is cooler than the land surface temperature. Now, if land gets cooler, then you will have a decrease in land-sea temperature contrast, correct? Because earlier, land was much hotter, but now you are introducing a term that will cool down the land surface, which means that there will be a decline in land-sea temperature contrast. So if there is a decline in land-sea temperature contrast, it will actually weaken and delay the land-sea breeze, correct? So the land-sea breeze will no longer come where it used to come before. It will be delayed, and at the same time it will also be weakened because land sea temperature contrast is now much weaker, and that should decline and delay in diurnal precipitation peak, and that is something which will be really exciting for maritime continent, because this should actually improve the model simulation because it will delay and weaken the diurnal cycle of precipitation. So we had to implement this particular mechanism into the model. So we are using a simple parameterization which is given by this formula. So basically the heat flux term is a function of specific heat of water. It's a rain rate, which is R, and the difference between surface temperature and the droplet temperature. Basically when the raindrops is touching the land surface. So that's what is the TR. So this is a very simple parameterization. We included this term in the model and then rerun the simulations to see how this term might actually impact the precipitation in the maritime continent. So we are doing two simulations. One is control and one is sensitivity experiment. I'm just calling it sense. So this one is without QP, and this one is basically with QP. So when we include this term in the model. So we ran it for two cases. One is April 2009, basically the same case that I earlier showed, and then another case which is June 2006. And the reason to choose those two times is because April 2009 was a very strong MJO, and June 2006 was actually a very weak MJO. So there was still a precipitation, but MJO was quite different in those two. And we are taking the outputs every 10 minutes. So this is very rare to take model output in this type of frequency. Normally people take it hourly or 3 hourly. And the reason we want very high frequency because we want to see if there was a change in timing in the precipitation in the maritime continent. Okay. So these are the two time period I just talked about, so I'll not get into that. And again, I'm using the moisture budget because our goal here is to explain what determines precipitation in the maritime continent. Okay. So our model domain is basically the whole domain here, but for all the results I'll show is within this particular box because that's where most of the Indonesian islands are, and we are interested in forecasting the precipitation over the islands. And two cases, one is strong MJO case and the one is weak MJO case. So this is really an interesting figure. What you are seeing here is that the black line is the observation, all right? And then red one is the control simulation, which does not have QP, and the blue line is the sensitivity simulation with QP. So what you notice first thing is that control simulation precipitation was larger, and that is a common model weakness that all models overestimate precipitation over land. And you can see that the red line is always above this black line. But when we introduce this QP term in the sense, you can see that the blue line actually came much closer to the black line. Okay. Now you might feel like, okay, this is not a big change, but this is actually a huge change. It is so difficult to get the diurnal cycle of precipitation in the maritime continent that even a small improvement is actually a huge achievement in some sense. And you can see the same thing happens here. This is your observation, the black line. The red line is without QP, and this blue line is with QP. So you can see that again it is coming closer to the observation compared to the control simulation. So there is, it turns out that QP actually has a tremendous impact over the maritime continent island. So just to summarize, diurnal peak in precipitation is earlier and stronger in control than observation. What I mean by this is that you see that the peak in the red line actually is earlier than the peak in the black line. So model actually has the weakness of giving earlier precipitation compared to observation. However, when we include QP, it actually reduces and delays the diurnal peak compared to the control. And this is something what we want to capture the diurnal cycle of precipitation in the maritime continent.